right? So now it's recorded.
Okay.
Thank you.
Okay, great. So my name is Pranav. I'm in the LXR team here in Boston. I noticed that the group has discussed a fair bit on transformers, starting from the vanilla transformer and then an amazing presentation on Transformer XL and then a few other presentations on BERT. So I thought in that spirit, we'll just talk about something that is very related, called the insertion transformer, which is in some sense based on and not based on the transformer really, because you can take the architecture. You don't really need to understand the transformer to understand how insertion transformer works. But yeah, so let's talk about that. Before we jump in, I just want to give you an outline of what this presentation is going to look like. We're going to start by introducing more like motivating the insertion transformer, and then we will touch a little bit on transformer. However, I'm not going to go into the technical details for a couple of reasons. At least one, because we already talked so much about it in the past few meetings. The second is for the lack of time. It's a humongous paper really, so to do merit to everything, to the important parts, I think I'm not going to go into the technical details. And then we're going to discuss the model, and finally, in the true spirit of machine learning, we're going to break it down into three parts. One is training the model. The second is how it works during inference, because there are a few things which are different. And finally, we will look at how it performs, the results themselves. And then, of course, we can have a discussion if we have time, if we have some time left. Yeah. So before I start, I'm remote, so there might be some lag between you trying to ask me questions, and if you're on chime and you're chiming me the questions, I don't really have a window open, so I wouldn't really know. So please feel free to just intervene or whatever. Okay? Yeah. So let me start with by introducing. So I think the key word here is autoregressive, really. An autoregressive model is one which uses observations from previous time steps as input. It basically uses observation from the previous time steps and passes it to a regression model to predict what comes next. Pretty much every neural sequence to sequence model so far, including the latest and the greatest, probably the transformer, is an autoregressive model, meaning that it takes everything that has been generated so far as input to a regression model, and it predicts one and only one output, which is the next word, essentially a language model, right? So there are a few things that might be considered as disadvantages with such a model. The first would be its inability to generate tokens in parallel, right? Because it's essentially a language model, so it still needs to produce word at a time step t before it can move on to time step t+1. The second is it does not accommodate for elaborate orderings. What does that even mean? Like a tree ordering, for instance. But the question is, why would you need such an elaborate ordering? So most of the work is done on machine translation, but I'm really interested in image captioning because it gives you a beautiful idea of why these elaborate orderings are important. So let's look at the image on the top, right? You have a cute little dog sitting in a hard drawn on a sandy beach. That's the caption. An RNN transformer would probably, an RNN or a transformer would probably go, the decoder would generate the sentence in that way. It would start with the beginning of sentence token. It would generate the word A, and then condition on these two, it would generate the word cute, and it would go on to generate the rest of the sentence. But let's think about how we process this image as humans. We do two things. We think fast and we think slow, right? We think fast and see a dog. We think slow and then we see a heart, and then we put together a beach, right? So we're not really coming up with the words cute little first before we come up with dog. We first come up with the word dog, the word heart, we see a beach, and then we start to add these adjectives to make it a more a comprehensive sentence, a sentence which describes the scene itself. So can we in some way have a model output or generate sentences in the same spirit, as opposed to restricting ourselves by having to produce the word a first. Just because we have a beginning of sentence symbol, we are pushing the model to start with the word a, right? You have this module networks and image captioning, which where every module is doing a different thing. The first module is probably looking for objects, the second module is looking for color, and so on. But it is not clear as to which module is being attended to at a given time step. So this is where elaborate orderings really help, where you need the flexibility to insert words at locations rather than only add words to an existing sentence. That is basically how I would motivate the insertion transformer. So let's look at an example. So the insertion transformer, or I will interchangeably use the word IT throughout, is inserting words into an existing, let's call it a canvas. A canvas is a sequence. These are interchangeable words. So we start with, when I say we start with an empty canvas, it simply means that the decoder hasn't generated anything so far. So at this point, what the insertion transformer does is it inserts the word 8. So as you can see, when it says 8, 0, it means the model is going to insert the word 8 at the 0th position. In the second time step, it inserts the word together, friends at the, together at the first position. But this is where it changes a little bit. At the fourth time step, rather, it can insert a word in the beginning of the sentence. It is not restricted to only insert words towards the end. So that is what it can do. But that is an example of serial generation. The cool thing about it, sort of new thing as well, is that it can generate words parallelly, in the sense that it's not restricted to generate only the word together when it sees 8. It can generate both friends and together in the same time step. So this is like a broad idea of what your model will do once you have built it. So let's look at the model itself. But before we do that, let's talk a little bit about the transformer, because, well, it has the word transformer in it, so let's do merit to it and talk a little bit about it. For this presentation, you can think of the transformer really as a black box which is mapping your words to a richer dimensional space. So, you have richer representations of your word because of a black box called the encoder transformer. That's all we need to know. But we will talk a little bit about attention, self-attention, and encoder-decoder attention, because the decoder is still important to us. And since the decoder uses these layers, let's talk a little bit about that. So the high-level view of these layers that you see in both the encoders. So the encoder is basically the purple-colored box, or the box to the bottom left corner, and the decoder is the I can use my mouse. Yeah, or the decoder is the box in the green, right? So the self-attention. Let's look at the decoder. The self-attention is essentially taking word representations and converting them to contextual word representations. That's how I would understand them. Why are they contextual? Because now this word is aware of what has been produced previously or what occurs previously. So this is important for it to give you some meaningful output when generating the next word. The second thing it does, it uses encoder-decoder. Now that it has contextual word representations, it's also just as important to know what input to attend to when producing the next word. Let's take image captioning again, right? So in image captioning, after the first self-attention layer, you know that the first two words that were generated were a cute little, right? The three were a cute little. This helps you get an idea that, the model knows that after a cute little, you would probably have a dog and not a truck, right? It gives you some sense of, the word representations are in such a dimension where this logic makes sense. But now it also needs to know that after a cute little, you should have the word dog, and probably not something like a cat. And this information needs to come from the image itself, which is where the encoder-decoder attention comes in. So after the encoder-decoder attention, you have context-aware, hopefully context-aware words, which are also aware of the image, which is important for this time step. Following that, you have some feed-forward layers. The way I understand this is, think about it, if you remove the feed-forward layer, there is no non-linearity in your entire system. So to induce non-linearity, to have some kind of transformation, non-linear transformation, you have a feed-forward layer, which is just taking the inputs, the embeddings that you have learned so far, which are in one space, and transforming them to another space. So for every, at the end of this decoder, for every word, you have a richer representation. That's like all we need to know for this presentation. At the end of the decoder, you have a richer representation of the word, and then you take this word and use it to predict the next word by passing it to a linear layer and then a softmax. So I'm going to stop for a minute, for a second actually, and ask you if you have any questions. Okay, great. I'll take that as a no. So moving on. Right. So the insertion transformer, as we discussed, is inserting words. That's where it is different. So the encoder is exactly the same, but the decoder has slightly new roles. While previously the decoder had to predict one word given a series of previous outputs, now the decoder needs to do two things. It needs to predict the next word, but it also needs to predict where the next word should be added, right? So it has two variables. One is the word which needs to be predicted itself. The second variable is the location at which the word needs to be inserted. So that's what the equation in the middle tries to capture. You have the decoder of the transformer model on the right, just so it's easy for us to draw parallels whenever needed. Right. So what I want you to take from this slide is that the insertion transformer is learning two variables. The first one is the word which comes next. The second variable is where this next word needs to be inserted. So these are the two things we want to learn throughout. And some terminology for the rest of the presentation is X, which is a source canvas. Source canvas is a source sequence. Y is T is the canvas at time step T, meaning that at time step T, these are the words which have been produced. Y itself is a target canvas or a target sequence, and L is the location. Location meaning location where the word would be inserted. A slot is basically an empty location, right? So if you have two words A and B, then the sentence AB has three slots. It has a slot before the word A, it has a slot between the words A and B, and it has a slot after the word B, right? So that's what a slot means. Let's take an example to see how this works. So at time step T, let's say you have two words B and D, and then your insertion transformer is given your canvas at time step T and also your input, and it predicts that C is the next word, and it should be inserted at the position 1. So your new canvas would be BCD because the word C was inserted at position 1. So that's how it's going to work. So the model would have so since we discussed transformer decoder, we can think about it in terms of how the transformer decoder itself is changed to accommodate for this new this new principles. You have in transformer you have a masked multi-head attention, where in this case you would have a full decoder self-attention. Why is that the case? It's simply because the canvas is, in the case of transformer as well as recurrent neural networks, you have hidden states which can be reused at every time step. In the case of a recurrent neural network, this hidden state is, well, your hidden state, the hidden state exactly, but in the case of transformer, it is basically the word representations of the previous time steps, which will not change as you go into the future. But unfortunately, that is not the case with the insertion transformer, because the ordering of the canvas itself is going to continuously change because you can insert words in the middle of what has already been generated. For that reason, you remove that masking. The second modification would be slot representations via concatenated outputs. So what does that mean? What you're doing is, instead of predicting a word, you're predicting what word goes into a slot, right? So now you have a concept of slots, and if your output has 5 words, then you will have 6 slots, which basically has 4 slots in between the words and 1 slot in the beginning and 1 slot towards the end. So you need to have, while previously you had n embeddings corresponding to n words, now you need to have n plus 1 embeddings corresponding to this n plus 1 slots, called slot representations. The way you would have your model to generate this n plus 1 slots is by taking your output and then concatenating the output so yeah, let's take an example. Let's say BD is the output canvas, which has 3 slots for insertion. So you would need 3 slot embeddings to be able to predict for each of the slots and then make a decision. So what you do is you take BD, you have a special symbol in the beginning of the sentence, you have a special symbol towards the end of the sentence. What this allows us to do is learn 4 different representations, and then we concatenate neighboring representations like E1, E2, E2, E3, and E3, E4. This leaves us with n plus 1 representations, each representation corresponding to a slot. The high-level understanding of why you concatenate E1 plus E2 can be thought of like this. Let's look at E2 plus E3. This corresponds to the slot in between B and D. Therefore, it's reasonable to assume that this representation is affected by the meanings of the word B and D. So it should be some kind of a combination of the representations of the word before and the word after. Therefore, E2 plus E3 can be thought of as a slot representation for the middle slot. And then we have a few model variants. What we discussed until now is basically how the decoder is different in terms of the input to the decoder, which is the slot representations, and in terms of how these inputs are, how self-attention is calculated. Now we'll discuss the model variants. So we talked about how at every time step your decoder predicts 2 things. It predicts the content and it also predicts the location. There are a couple of ways in which we can do this. So there are a couple of matrices that will be used. So I just put them up there. The first one is H, which is essentially the hidden representation of every token or every slot. So hence T plus 1, where T is the number of tokens, and W is basically your matrix projection, which takes which you use before your softmax, so that you can map it to the vocabulary. So if you have C words, then you want to map your hidden representation to C so that you can predict the next word. That's what W is. Now we need to predict the joint distribution, which captures word and a given location. So when I say PCL, it means probability that a word X goes into a location Y. That's what PCL does. And we can calculate this in 2 ways. One is through modeling it through joint distribution. So we are essentially just going to flatten the matrix that we get by multiplying H and W. So if you want to visualize it, it's essentially it has T plus 1 multiplied by C dimensions. So each of those corresponds to a slot and a word and a location. If you simply take a softmax of that and take an argmax, so you're essentially choosing a slot and a word and a slot, which will be filled by the insertion transformer. The other way to do this is to use conditional distribution, where you model joint distribution of C and L as conditional distribution of C given L and the probability of L itself, which are both very straightforward. There are a couple of equations down there which are which kind of give you an idea of how you do it. It's not really important, but it's very straightforward, so I'm going to skip it. So the other variants are contextualized vocabulary bias and mixture of softmax's output layer. So these are all different ways in which you can learn this joint distribution and also still be efficient. That's what mixture of softmax's does, where you perform k softmaxes. Let's say you do a softmax over the content and you do a softmax over the location, and then you combine them using some tricks. Again, this is like an entire paper in itself, so I'm not going to go into that. But what is important for us is that table where they do an ablation study of the different approaches. What works best for them is to use a joint distribution with the mixture of softmaxes, I guess. Yeah. Yep. Should I stop for a minute?
Sorry, but here I have a question. So for the first row in this table, in this table 2, the first row, so it means that none of these tricks is used?
Yeah, so that's probably the baseline.
Okay.
That's probably the baseline where they're not really predicting multiple words in a slot.
Okay, I see. So this corresponds to the model without the inversion transformer?
I believe so, yeah. So good question. I'm not entirely sure, but that is my guess.
Okay.
Yeah. Okay, so let's talk about training now. So there are three things that there are three ways in which we can generate these orderings. The main thing that the insertion transformer introduces is the flexibility of having orderings which are different from a left to right ordering. So a left to right ordering is basically a vanilla transformer, so the left to right generation is basically one token at a time. So you don't really need to change your loss function significantly. It's the exact same loss function as you use in a transformer. But if you want to do where it gets interesting is the balanced binary tree, where you're doing multiple insertions. And as the example shows, let's say you have an output A, B, C, D, E, F, G. So what you would want to do is you would want to predict the words in the middle, and you want to branch outwards. It's basically like your binary search, right? So you want to predict the middle word D, and then you want to branch outwards. So in the remaining 4 slots to the left, and 3 slots to the left and 3 slots to the right, you want to train your model to predict the word in the middle. So that is the enforcement that is the kind of knowledge that we want to enforce the model with. We'd probably like to think of it like this, right? So maybe you want to train the model to learn an inductive bias, which is assuming that predicting words in the middle gives you A, content, B, it helps you it also helps you branch out and predict words to the left and words to the right. I'm guessing that is an inductive bias, which is really what makes a model to be on par with transformer. So this is what you're trying to train the model to do when you're using a balanced binary tree loss. The way you would do it is by using. So this is the crux of I would say crux of the on the paper, probably how they design the loss function, and it's best to work it backwards. So let's look at the last equation. The last equation is basically the sum of the negative log likelihoods. So for a given slot, you basically find this negative log likelihood with respect to everything in its span. So a span for a slot is defined as a series of words which are potential candidates for that slot. So what you want to do is for each of those words, let's say for instance, if you are predicting something in bit, something to the left of D, then your span would probably be A, B, C, D, right? So and now you want to condition your model to predict B with a higher probability than A. So the way you would do that is by giving it a higher weight. That's where W comes in. You want to give a word a higher weight if it is towards the center. So you need a metric which captures the distance of a word from the center of the span. That metric is called DL. So DL is calculated exactly how I defined it. So basically IJ plus JL is by 2 is the center of the span. And when you subtract I from it, it basically gives you the distance of the current word from the center of that span. And if that distance is low, then you want to give it a higher reward. So what they do is they use the negative of this distance as the as the reward in like a softmax policy, which is the second equation. So let me stop for a second and make sure that makes sense. Okay, great. Right. So basically, you sum up the negative log likelihood with respect to all the words in the span corresponding to one slot, and you weigh it with respect to the importance of every word, because in this specific balanced binary tree loss, you want to give a higher weight to words in the middle than to the ones in the peripheries. So that's where WLI comes in. This gives us a nice segue into the next loss, which is the uniform loss, where you don't want to make such a distinction. You don't want to make a distinction between the word in the center or words towards the peripheries. So instead of having in the last equation, instead of multiplying the sum of the negative log likelihoods with a weight associated with every word, you will simply take a mean of all the words in the span. That is the only difference between the binary tree loss and the uniform loss. And this is like a visualization of how how the weights associated with tokens change with one loss as opposed to the other. So if I were to like interpret this diagram, I would say that with the balanced binary tree loss as expected. In fact, since we optimized for it, it's no surprise. But anyway, I would interpret it as the words in the middle have a higher weight associated with the binary tree loss. But if you look at the words in the peripheries, then the uniform or the balanced binary tree loss don't really make a distinction between these words. Right, so those are the loss functions, which are sort of crux because they enforce a certain kind of ordering. So now that you have trained the model, now you want to use the model during inference, right? So there are a couple of things we can do. The first is greedy decoding, where we learn the joint probability distribution of C and L, which is the word and the location, and we simply pick the pair with the highest probability, meaning that if the word dog should occur, if the pair the word dog should occur at location 4 has the highest probability amongst all the generated pairs, then we simply insert the word dog into the 4th position and move on. What makes it truly partially autoregressive is the ability to do parallel decoding instead, which is the second option, where you can add multiple words in the same time step. What we do here is for every slot, we predict a word. So when we're doing that, we can think of this as fixing the location, which is why it is conditioned on the location as well. So you're fixing a location, which is a slot, and for each of the slots, you predict a word. And once you have predictions for every slot, you're going to populate them with the new predictions if and only if the slot is not an end of sentence token. If it is, then you just leave it, as in you don't populate that slot, and then you generate the output hypothesis, which is used as an input to the next time step. So this continues until every slot has been filled, and the all predictions for all slots are end of token symbols, which means that the sequence itself has ended. So the way I would understand this is, instead of learning a joint distribution of location and content, let's just learn content for every slot and take the argmax of the content for every slot and populate every slot simultaneously. So that's how parallel decoding is done. Before I get into the results, which is like mostly just contemplative, I guess, are there any questions on the model, or like how it works or why it works? All right, great. So there are two kinds of decoding as we discussed, but let's look at the parallel decoding because that's what generates the best results. Yeah, so it's basically predicting words. At least it is conditioned to be biased towards the words in the middle. These are obviously cherry-picked examples, which is why the words predicted in every time step are perfectly in the middle. So the number of iterations you have are perfectly log n. That doesn't happen all the time, but more often than not it does. We'll look at a graph which discusses that more. So the first one is a binary tree loss. The second one is a uniform loss, where it's not necessarily biased towards the words in the middle. It just learns that the word. It's interesting to see that even though it's not biased towards the words in the middle, it still learns words inside the sentence rather than on the peripheries, which kind of reinforces our initial assumption that words in the middle are probably where the crux of the sentence is, probably maybe. So that's just an interpretation from of the results. And the first metric to gauge the success of the insertion transformer is the number of decoding iterations, which is log n compared to the number of decoding iterations from the transformer. So what you see there is the solid line is the upper bound, which is n iterations which any recurrent neural network or transformer is going to take, and the lower bound or the red line is log n, which is the best case scenario, and the insertion transformer with the binary tree loss is very close to the lower bound. So yeah, I think that's one success. And the other metric is obviously the blue score, because they're evaluating this on a machine translation task. So as you can see, what works best is the insertion transformer with the binary tree loss is as good as in terms of results, it is as good as the transformer model, but it does this with log n number of decoding. So a magnitude smaller than the number of decodings your transformer model requires. Yeah, that's pretty much it. So in case you're interested, what BERT is to transformers, there's Kermit is to insertion transformers, I guess. I recently came across Kermit, so if you're interested, take a look at that. I'll add a link to it after the presentation. I couldn't find the link. So yeah, and I had a few things, few points which were of interest to me. But before I delve into that, like, are there any questions?
Okay. Yeah, so for the Kermit paper, it's like to apply this insertion transformer for the BERT-like structure to.
Correct.
Yeah. Okay.
Yeah. Yeah, and a few things that were of interest to me was applying this to image captioning, and I would really like to superimpose every word predicted onto the attended part of the image, which would tell you how you attend to an image as opposed to the model itself. And as an extension, it would be really interesting if you could have an eye tracking experiment with some participants to understand how we decode a scene differently from a model, right? Or maybe we don't when we use the insertion transformer. Meaning that like I discussed in the beginning, when we decode a scene, we are thinking fast and slow. So the way we attend to a scene is we probably look at something in the middle, something that is big or something that is bright, and we tend to branch out into the rest of the scene. So if you have an eye tracking experiment, you can see how our attention varies across the image throughout the through a sequence of time steps, and then you can also see how uh, the model starts captioning. So you can know that it will be like a super interesting experiment as far as I'm concerned, because it can tell you how the model attends differently from the human eye. And I would expect very different kind of attention map, because we have very different cognitive biases, right? We have inherent biases which are very difficult to train to a model only from a limited amount of data. So I think that is something that's very interesting. Also, we see that there's a decrease in the number of decoding iterations, but we don't really know if this translates to a decrease in the wall clock time. So I think that is something that we need to figure out empirically from experiments, but I think that's probably more important than just a theoretical estimate on the number of iterations. So these are a few things that I was thinking about when I read the paper.
Yes, in fact, for the first part, in terms of yeah, so for the image generation, I think there was a rather old paper called Draw. So it's generating MNIST images by updating a canvas. So it's like so in the first step, the canvas is empty, and then at one step it will put something in the canvas to draw it to update the canvas iteratively and finally get the output. So actually I have sent the link of this paper. So
Oh,
it's
interesting.
yes, it's a somewhat old paper, but I think it's one of the initial paper that proposed to use the idea of neural attention to image uh, yes, to generate the images. So yes, so that would be related, and mm, uh, yes, and another thing is, in fact, for this like image captioning and attention, so we have this show, attend, and tell, which is also like some famous paper, I think. So it's uh, so I think in the initial image captioning paper, people are looking at how the captioning will be related to certain parts of the.
That's true, but the thing with show, attend, and tell is that there are two kinds of attention, two kinds of visualization. One is post hoc interpretability, and there is post hoc interpretability is when you build a model, you do inference, and then you look back and say that this is the word we predict because the model was looking at this part of the image. Show,
Yeah.
attend, and tell, and and then the things which came later were all mostly looking at post hoc interpretability, where you can know that a word was outputted because a certain part of the image was attended to. But it is also interesting to know if the scene with the highest attention is the word you're attending, is the word you're outputting first, right? So for instance, in the case with the dog, right, the dog is probably the one with the highest attention. Maybe, I mean, that doesn't make sense. I mean, the dog is the one where uh, in our case we have a higher attention for the word a in the first time step. But I guess my point is that as humans don't really do that. We have in our first time step, we don't look at the word a, we look at the object itself, we attend to the object, and then we fill the rest of the gaps. But the model, what Shwetan and Dell or any image captioning model currently does, it uses a simple language model where it has a high attention towards words like A in the beginning time steps. And as you go into the middle, that's when the attention shifts towards the main part of the image. So that would be interesting to see, is what I was getting at.
Yeah. I think applying this insertion transformer to image captioning has the potential to improve the overall accuracy. I think. Yes. Yes, I think it will generate a more meaningful attention sequence than the naive sequential approach.
Right.
Yeah, and also I think I think in the paper I think one advantage of this insertion transformer is that due to the parallel decoding, it is potentially much faster for the machine translation task if the source and target sentences are very long. So
Yeah.
because yes, because in the decoding phase, usually we require O(n) steps, and now we can reduce it to O log n steps. So that means it will be potentially useful for document level machine translation. I think because
I see.
the documents are very long, it consists of several sentences. So I guess it will be useful to do this insertion transforming.
Makes sense. Yeah.
And also for this paper, I find that for both the binary tree loss and the uniform loss, we will need to have the idea of this central words. So I think that is not like very reasonable for me because why should we focus more on the center? I mean, if we think of this problem from the semantic perspective, I think there are some cases that the center word is not representative enough of the whole sentence. But I think in their formulation they rely heavily on the definition of the center of the sentence in order for the whole insertion transformer to work. So maybe it's possible to lose this constraint. So we can like first choose the center and then so maybe for the first step we choose our starting point.
But that's what gives it the computational advantage, right? So if you the fact that you're able to predict the center word has, I think, a couple of implications. One is that they believe it's important. The second is that it helps you reduce the number of time steps. If you weren't predicting the center word, then you will not be reducing the decoding iteration from big O of n to big O of log n, right?
Yeah, that's true. So yes, what I have proposed the same as a uniform uh, uniform variant proposing that in this paper, because I think for the uniform one, it has not used the center word, right?
Right.
But I think in the examples in the figure 4 of the paper, even for the uniform loss, it always start with the center word. So I'm not very sure about this part.
Yeah, I mean that's what I thought as well. I mean the words are not necessarily in the center, but they're definitely in the middle as opposed to something in the peripheries. I assume that was just a consequence of the words in the middle being more content heavy. Again, I don't have
I,
a concrete.
I
So
think
looking at
that figure 4, the lower sentence, which is uniform, actually I find that the words that are selected which, as you said, are in the middle, are actually not very content heavy. So it's a German sentence, and these words that are selected are pronouns, or articles. So that's
my point was actually going to be the same. I think it's very language dependent, and I think that because English tends to be that way, that's why they selected it. But I think for a language like that has less like fluff words, I think it would be a lot harder to, or it would be less accurate.
right. But the argument here was that if we have the uniform loss, then we expect the model to select maybe very content-heavy words first. But then what we observe in that figure is that it actually does not select any content-heavy words, but rather selects very general words that fit in any sentence, essentially.
That's interesting. So the authors themselves don't make an argument as to why the uniform. So what they do say, I'm just doing a quote unquote of why uniform loss is important. They think that the neutral approach, meaning the uniform loss, is useful as it forces the model to be aware of all the valid actions during each step of the decoding, providing a rich learning signal during training and maximizing robustness. That's how they put it. So they don't claim that it's moving towards content heavy words, but I'm just trying to interpret the results, and I felt that since the words in the middle were being decoded first, I assumed those were content heavy. But like you mentioned, looks like that's not the case. So I'm not really sure why those words are being attended to first.
I think the reason why it's predicting those words is not because of the crux of the sentence. It's more that it allows it to predict outwards, if that makes sense.
That makes sense. Yeah, that's what I was wondering as well. That makes sense.
I don't think it's necessarily that it's content heavy.
Yeah, that actually makes sense. Yeah.
Yeah. Okay. Yeah.
If there was a way to do the content heavy thing, then I also agree with your hypothesis with the image captioning. But at the moment, I don't think this is gonna change the image captioning thing.
So
Sorry for my voice.
I have one more thing to add to this figure 4. So what I find very interesting is that, as I mentioned before, these are articles that are being generated first, and in German, actually, the spelling of the article depends a lot on the following word, for example, on its gender, or other properties of that word. And therefore, in this case, when the model first generates the article, it must already have decided is the next word it wants to generate. So it seems like the causal structure is inversed here. The model first generates the word it should generate afterwards. So it's very strange to see
I see.
order that the model chooses. But that's how it does. But maybe we can, I don't know, have another loss that would find a more meaningful order. I'm not sure. This is just something to note based on the German language here.
Yeah, so maybe I think it's better to interpret the model as like how to accelerate the decoding phase. Maybe that's the more fair interpretation.
I
of
think
this.
that's the biggest contribution.
Yes.
The fact that it can generate faster.
Yes, in fact, if
Yeah, in fact, the model is not. It doesn't claim the model is better in any sense. Like the accuracy is in it. If nothing else, it's worse than the transformer without a few tricks. So it doesn't really have any improvements in terms of accuracy. Like you said, it's mostly its ability to generate faster and in parallel.
So do you think there will be some possible approach that we can make it more semantically meaningful for this kind of insertion based generation? I think that depends on the structure, maybe the semantic and the syntax structure of the sentence. So
I think this is trying to mimic the syntactic structure by going for that middle point, and I don't think it does that accurately.
yeah, so maybe if now let's assume that maybe we can get the syntax structure. So
So you have like a knowledge base?
maybe
before?
we can like maybe we can like use that information to guide this kind of insertion steps. Maybe that's also possible. Like to have some auxiliary laws to guide this insertion softmax to yeah to
I just think it's a problem with that, at the weighting function. I think that weighting function, because it's going only for that middle thing, I think that's the biggest problem. If there was some way to change that weight function so it was more meaningful, that would have an effect, but it may also kill the performance.
Yes. Also, I think for the second point, the discussion phase, I think it will be really cool if we can do some experiments.
So if you search visual saliency, there are a lot of people that have. So I worked on a project briefly on visual saliency, basically where people look in an image first, and it didn't really tend to be at objects or anything. It was at the thing that was most colorful.
Okay.
So it really wasn't. I don't know if it'll be the most helpful to do something like that and look at how a human does, because I would also argue on that first image with the dog. I just focus on the dog. I wouldn't even look at I wouldn't recognize beach in the heart as my like secondary things. It would be dog, then cute and little, and then I'd think about heart and beach.
I think it's more of an experimental setup. So it depends very much on the experimental setup. If you ask your Turk workers or your participants to give you a detailed description, then it's all right. Like you said, they're probably not going to mention the beach, but that's the best part, right? So you're not interested in what they say right away. You're interested in how they describe a scene over a period of time. You want to see what they include after some time, right? So I'm assuming that these peripheral things that, like you said, beach, which are not really important, if the experimental setup requires them to like stick to these constraints where it has to describe, let's say, every object or something like that, it can give you an idea of in which time step they really think about these peripheral objects. That is really what the experiment is trying to elicit.
But wouldn't you say that like it's very paramount in an image that you know the setting of the image? So I would actually argue that a machine looking at the beach first is actually better, even though a human might not necessarily think about it.
In fact, I think the human brain is like it's very easy to fuse the human brain because that's how the magic works. So actually, for when you play some tricks in the magic, you are actually guiding the attention of the human eyes. So it's like sometimes you can use some like colorful objects to guide the salient point of the human attention. Actually, I think that's previously I watched one video in Scientific America, and they explain how the magicians tricks your brain. So actually, that's related to
also.
Yes.
So with video capture and stuff like that, I mean, we were trained like biologically to look for motion. So we're always going to follow motion rather than something that's still or very small amount of motion.
So maybe designing some machine learning model that tries to mimic how the brain works does not make sense to actually solve the problem. But nevertheless, it will be interesting to do some experiments to see how. But I personally disagree with the idea that we should mimic how the brain works.
I agree with that.
Yeah, that's reasonable. I don't think we should agree with we should mimic everything that the brain does. But I think what the second experiment can do is tell you how they're different, and from the differences you can decide whether to. There are two things, right? You can either take some things from the brain and help make your model better, or you can look at the model itself and then see what it does better than the brain. That gives you some understanding of what it's doing different. That's what I was looking at, and that's the direction in which I was thinking about it. But what you said makes perfect sense. I don't think we should just be mimicking it for the exact reasons you mentioned.
Yes. Yeah. Okay.
It's 10:30.
Yeah. So any other questions from the chat?
What time period did this come in? Was this before XLNet? And was this like what? Did it just get released?
February, I think.
Okay.
Feb.
Yeah, it says Feb.
Yeah. Is there any other comments, like questions or discussions from the chime? Okay, so if that's the case, so thank you, Pranav, for the presentation.
Yeah. Thanks.
Thank you.
Thanks.
Thank you.
Thank
It was
you.
really good.